Hello, my name is Dmitrii Marin. In this talk I will introduce token pooling, which is a pooling method designed for vision transformers. Pooling is a commonly used method to improve the computational efficiency of CNNs. We design a new pooling layer to improve the performance of vision transformers. Let me give you a quick peek of our main results. Here we analyze the computation accuracy trade-off of a standard vision transformer by varying the number of features. The x-axis is the computation in flops, and the y-axis is the top one accuracy on the ImageNet dataset. In this plot, better models approach the top left corner, higher accuracy with lower flops. We applied our token pooling layer on DeiT, significantly improving its performance. For example, we can achieve the same accuracy of DeiT-Ti while using 42% less computation. Or we can choose to use the same computation while improving the accuracy by 3 points. Let's first recall the architecture of transformers. A typical transformer block is composed of multi-head attention layer and MLP. It takes n input tokens and outputs the same number of tokens. Many such blocks sequentially transform the tokens, keeping the number of tokens unchanged. Vision transformers are simply transformers where the initial tokens are made of image patches. To use token pooling, we take a standard transformer and add the pooling layer after each transformer block, just like the pooling layers in the CNNs. The pooling layer takes the input tokens and outputs fewer tokens as shown on the slide. This means that the next layers only need to process a smaller number of tokens, so they need less computation. The second token pooling will further reduce the number of tokens, and so on. Notice that we are processing fewer and fewer tokens. This compound effect is one of the reasons why pooling layer improves computational efficiency. Now let's see how we design token pooling. Since we reduce the number of tokens, we will lose information. An important question is, how do we select the tokens so that we can best retain the accuracy? Just like most downsampling algorithms, we need to identify redundant information and try to prune it. This means that we should drop redundant tokens. One of the main contributions of our work is that we show that transformers, by construction, produce redundant tokens. Specifically, we show that the softmax attention is a low-pass filter applied on the input tokens. In other words, its output tokens will have similar values that can be pruned. We also show that tokens are discrete samples of a continuous signal. This perspective is important because it allows us to apply non-uniform sampling literature. The most effective tokens to keep are the tokens that minimize the reconstruction loss. Therefore, we design token pooling to minimize the reconstruction loss. Here is the algorithm of token pooling. In order to output a smaller number of tokens, we first cluster n tokens into k clusters. Then we return the average of the tokens belonging to each cluster. We found that the k-Medoids approach produces the best computation accuracy trade-off. This is a simple algorithm, but as shown in the paper is effective. This concludes my talk. You can find more information and results in our paper at the link.